Welcome back to Applied AI Engineer. So far our agent is brilliant for exactly one turn, and then it forgets you completely. Today we fix that. We give Atlas memory to carry context across turns, to distill a long conversation down to its essence and, crucially, to remember even after the process is killed and restarted. By the end, Atlas will recall what you told it 3 turns ago, recognize you by name, and pick up exactly where it left off after a restart. Memory is what turns a clever demo into something that feels like an assistant. Last episode we built a multi-agent system, a planner worker graph in LangGraph, with subagents handing work to each other and a human-in-the-loop interrupt. That graph could reason across nodes, but the moment a run finished, everything it learned evaporated. Today we keep the same graph machinery and bolt on the missing piece, memory, making Atlas remember within a conversation, persisting that memory to disk so it survives a restart, and summarizing old history so the prompt never blows the context window. Here's the uncomfortable callback to episode 1. The model API is stateless. It does not remember your last message, your name, or anything else. Each call starts from a blank slate. Everything that feels like memory in a chat product is an illusion that you, the engineer, maintain. You store the conversation and replay the relevant parts on every turn. So memory isn't a model feature you switch on, it's a system you design. The real questions are what to keep verbatim, what to compress, and what to throw away. Think of memory in 2 layers. Short-term memory is the recent window of turns, kept word for word, fast and exact, but every message eats into your context budget and your bill. Long-term memory is the distillate, older turns compressed into a short summary, plus durable facts about the user like their name and tech stack, compact, cheap, and it survives forever. A good agent runs both, a small verbatim window riding on a steadily updated summary. We'll build exactly this for Atlas. Let's start with the simplest, most important kind of memory, remembering within a single conversation. In LangGraph this is beautifully clean, because the graph already has a state object. We just need that state to persist between invocations rather than reset each time. Here's the shape of Atlas's memory, a typed dictionary with 3 fields. Messages is the short-term window of recent turns. Summary is our long-term memory, where older turns get folded. And profile holds durable facts about this specific user. The interesting part is that little reducer on messages. A LangGraph reducer decides how a node's output is merged into existing state. Ours appends when a node returns a plain list, but replaces the whole window when it returns a set command, and we'll need that replace power the moment we start summarizing. This is the heart of it. Every turn, the respond node takes the last few messages, the window, and builds a prompt. Notice how memory enters the model, the profile and running summary go into the system prompt, the recent turns into the user prompt. The model never magically remembers. We hand it the memory on every call. The reply is appended to messages, and that returned dictionary is what LangGraph checkpoints. The graph itself is deliberately tiny, a single respond node between start and end. That's intentional. Today's lesson isn't graph topology, it's state. The magic is the last comment. When we compile with a checkpointer, that same one-node graph becomes stateful. Every invocation now loads the prior state, runs, and saves the result, and from the node's point of view, nothing changed. Memory is a property of how we compile, not how we wire. Now we drive it. The ask helper invokes the graph with one new user message and a config carrying a thread ID. That thread ID is the single most important idea here. It's the key under which all of this user's memory is stored and retrieved. We compile with a checkpointer and seed one durable fact using update state, which writes straight into the persisted profile. From here, every call to ask just adds a turn. The memory takes care of itself. Here is a real, unedited 3-turn run. Turn 1 at last greets the user by name, Mahesh, because the profile fact flowed into the system prompt. Turn 2 answers a technical question in character. But turn 3 is the proof. We ask what the first thing we told it was, and it correctly recalls wiring memory into your agent today. No global variable holds that. The conversation flowed turn to turn purely through checkpoint state, keyed by thread ID. Remembering within a session is table stakes. The real test of a production agent is this: kill the process, start it again tomorrow, can it still pick up the thread? In-memory state can't. We need checkpoints written to disk, and LangGraph gives us exactly the right scene. A checkpointer is a LangGraph object with one job. After every step, it saves the complete state, filed under that conversation's thread ID. LangGraph ships an in-memory checkpointer that's perfect for a single run, but it lives in RAM, so when the process exits, the memory is gone. For at last to remember across restarts, we need a checkpointer that writes those same checkpoints to disk and reloads them on startup. The beauty is that the graph code doesn't change one line. Only the storage behind the checkpointer does. Here's the smallest honest fix. Our filesaver subclass LangGraph's in-memory checkpointer, so the graph talks to it exactly as before. The additions are at the edges. In the constructor, if a save file already exists, we load it back into the saver's internal dictionaries. That's the restore. The serialized format is whatever LangGraph itself uses, so what we reload is byte for byte the state we saved. We also take a lock, because LangGraph writes from worker threads. And here's the save side. We override put, the method LangGraph calls to record a checkpoint, let the parent do its in-memory store, then flush to disk. Two production details matter. First, the lock checkpoints can be written concurrently from executor threads, so we serialize the writes. Second, we write to a temp file and atomically replace the real one, so a crash mid-write can never leave a corrupt save. Small touches, but they separate durable from merely hopeful. Here's the whole persistence story in one picture. Process A runs the session, each invoke changes the state, and on every checkpoint the saver writes it to atlasmemory.pkl, keyed by thread ID. Then the process exits, the line is broken, no shared memory left. Later, process B starts fresh, and the filesaver constructor loads that same file. Same thread ID, same state, Atlas wakes up remembering turn 1. The only thing connecting the two processes is the file on disk, exactly how real persistence should feel. Now the payoff, and it's genuinely satisfying. This is a completely separate process. Session.py ran, exited, and now resume.py starts cold. Before asking anything, it reports what it loaded from disk, 6 turns and the full profile. Then we ask a fresh question, and Atlas answers with our name, what we are building, even what we were doing, all reconstructed from the checkpoint file. Nothing was shared in memory between the runs. The agent's mind was rebuilt entirely from disk. There's a problem lurking in everything we've built. If we keep every turn verbatim forever, the conversation grows without bound, and since we resend it every call, cost and latency creep up on every message, until eventually we blow the context window. The fix is long-term memory. Compress the old turns into a short summary and keep only a small verbatim window. Why bother summarizing? Because you pay for every token you resend on every turn. A conversation that grows verbatim is a bill and a latency curve that climbs without end until one day the prompt doesn't fit. The standard fix is a rolling summary. Once the window grows past a limit, fold the oldest turns into 2 or 3 sentences, keep the last couple word forward, and carry that summary forward. It becomes durable long-term memory, small, cheap, coherent. Here's the summarizer. When the window overflows, we split it, keep the last turns verbatim, take everything older, and ask the model to fold those lines into an updated summary that also incorporates the previous one. That last line is where our reducer earns its keep. We return the new summary and return messages as a set command, which tells the reducer to replace the window rather than append. So the old turns physically leave the prompt, but their meaning survives in the summary. And it works. We fed Atlas a technical thread about migrating its vector store 8 messages deep. After summarizing, the window is back to 2 messages, but look at the summary. It captured pagevector, the voyage embeddings, the chunk size and overlap, the cross-encoder re-ranking. Every important fact survived, only the verbose phrasing was dropped. From here the prompt stays small and steady however long the conversation runs. That's long-term memory, working for real. Visually, summarization looks like this. On the left the window keeps growing, turn after turn, until it overflows and cost and latency climb with it. The model folds the old turns into one compact summary on the right, and we keep just the last couple of turns verbatim beside it. The prompt is now bounded, a short summary plus a tiny window, holding the same information. We compressed the conversation, we did not forget it. This is the move that lets an agent hold a genuinely long relationship with a user. One last piece makes this real for production. A deployed Atlas serves many people at once, and Mahesh's memory must never leak into Asha's conversation. We've already solved this, it falls right out of the thread ID, but it's worth making explicit, because it's where a lot of naive memory implementations go wrong. The thread ID we've been passing is also the isolation boundary. Every field, messages, summary, profile is namespaced under it. So the same compiled graph, with no code changes, serves thousands of users, pass a different thread ID, and the checkpointer loads that person's memory and nobody else's. A common scheme is user:_id, or user:_id:conversation if one user has several chats. The model remains gloriously stateless. The checkpointer quietly holds everyone's state, cleanly partitioned. Here's that isolation as a picture. The model in the middle is stateless, it holds nothing between calls. Underneath, the checkpointer keeps a separate, sealed memory for each thread ID, Mahesh on Python, Asha on Go, Dev on Rust. Same graph, same code, 3 independent minds. Switching users is just switching the thread ID you pass at invoke time, how a single deployed agent gives every user a private, persistent relationship. And this pattern isn't specific to our file saver. OpenAI's Assistance API offers managed threads that keep memory server-side under a thread ID, same mental model, just hosted. LangGraph itself ships database-backed checkpointers, the SQLite and Postgres savers, with the identical interface. Swap one line and your memory lives in a real database. And for very long histories, teams embed past turns into a vector store and retrieve only the relevant ones, memory as RAG. Different storage, one universal pattern, a thread key plus a store you control. A few traps catch people every time. First, an unbounded window, resending an ever-growing transcript until cost explodes or the context overflows. Always cap it. Second, the opposite, summarizing too aggressively, so you lose the recent detail the user actually cares about. Third, a quiet security bug, profiles and summaries can end up in logs, so never let secrets drift into long-term memory. And fourth, the one we engineered around today, forgetting to flush, so your in-memory state evaporates the instant the process restarts. Lock in the mental checklist, because you'll apply it on every agent from here. Keep a bounded short-term window so recent turns stay exact. Maintain long-term memory as a rolling summary plus durable facts about the user. Persist checkpoints to disk or a database, so a restart doesn't wipe the relationship. And isolate every user strictly by thread ID. Get these 4 right and your agent feels less like a stateless function call and far more like an assistant that actually knows you. Quick recap. Memory is not a model feature, it's state you store and replay, because the API itself forgets everything. We built at LAS a short-term window, a long-term rolling summary, and a durable per-user profile. We gave it a disk-backed checkpointer so it survives a restart, and isolated every user by thread ID. Atlas is now genuinely stateful. Next episode opens the production module, the one that separates demos from shipped software, evaluating LLM apps. We'll build an eval harness with golden datasets, an LLM judge, and regression tests, so we can prove Atlas works, not just hope it did. See you there.